Manif, and this is my lab floor report on springs and oscillations for Physics 2211. So in this video, I'll go over the introduction, the purpose of the lab, some formulas we'll use, our experiment and data, our glow script and model, the discussion of possible errors, and our conclusion. So the purpose of this lab is to observe a spring mass system where the mass is oscillating in an arc shape. We then use Tracker to plot the position of the mass and create an Excel sheet with the relative x and y positions. We will then create a computational model in glow script to predict the graph and the object's motion and energy changes. So some things we'll visit in this lab is the energy principle, Newton's second law. So Newton's second law says the system change in momentum is proportional to the net force applied. The energy principle here would say the system change in energy is the sum of work done by the surroundings and thermal and energy exchanges. So some formulas we'll use is going to be the force model here, our momentum and our position update formula basically, and our energy principle stuff here about, K equals 1/2 mv squared, our energy conservation stuff here. So the spring force here is always along the spring axis. Gravity only changes the vertical component. Tracking the energy terms let us test whether total energy stays almost constant. And here energy is equal to 0 because it's conserved. So here is my tracker. As you can see, I uploaded the video to tracker and plotted the motion using AutoTrack. I copied the X and Y column data into the Excel and exported it as a .csv file. I calculated the initial conditions using the tracker data to find initial position, velocity, spring constant, and resting length. And then I used the .csv file in glow script. So here is my glow script analysis. Here's my constants and stuff. Here's the mass of the ball is 0.402. The gravity is this. Spring constant was calculated using the periods here. And so it was our resting length. And our ball position vector was calculated with this first change right here. Our system is Earth, mass, spring, and surroundings and sun. So here's a glow script analysis, a code analysis. Here I compute the spring direction and length, and I calculate all energies, kinetic, gravitational, spring, and total. This also updates the spring visualization and plots the initial model versus tracker positions. Here I calculate the forces, gravity plus spring, and I apply Newton's second law of motion, Newton's second law to update the motion. I also recompute energies for each step and track how they change to check the energy conservation. And then here, I plot the model against experimental tracker data over time, and then I get the steps through tracker points, and then the correct rate and update the simulation time until it's finished. So here are my graphs. This is my x position versus time. Here's my y position versus time graphs. And as you can see, my model resembles it very close to the tracker data. Some sources of error we can run into is limited precision when rounding, human error for picking inaccurate values, and then it's not an isolated system, so work can be done by the surroundings. So is the energy principle satisfied? Yes, the energy principle is satisfied. We can see that there's no external forces which affect the system, so the net change in energy must remain 0. Even though there are different types of energies in the system like gravity and spring, the graph still shows the total change in energy is constantly 0. The orange line remains flat. So you can see that gravity is canceled out by spring, and additionally spring is canceled out by delta K. Everything gets canceled out to 0. And our estimations of oscillation data. So in the x direction, I calculated it to be 5.82 Newton meters. And then in the y direction, I calculated it to be 6.83 Newton meters. And then our time step is 1.524 seconds for y direction, and then 1.651 seconds for the x direction. The y direction value is probably a better estimate since it matches the spring constant I was given earlier, and the oscillations in that direction is usually easier to measure more cleanly. In conclusion, the computational model successfully predicts the motion of the spring mass system. The results support both Newton's second law and the energy principle, and the model closely matches my experimental data. Thank you.